हसतो सकमया तमसो मा ज्योतिर्गमया मृत्योर्मृतं गमया ॐ शान्ति शान्ति शान्तिः.
Very good evening to all the mathematics enthusiasts present here. It gives me great pleasure to welcome you all to the 16th Math Ecstasy webinar on the National Mathematics Day conducted by Maths Aspirants Group. As you all know, Maths Aspirants Group was started in the year 2017 by Dr. Vinod Kumar P. He's an associate professor at TMG College, Kerala. And it was started with a few students and teachers to discuss mathematics. But right now, 8 years have passed, and now Maths Aspirants consists of 6 WhatsApp groups, 1 Telegram group, and a Google group with educators and learners across the world. It also has become a platform to discuss, learn, and relearn mathematics, and has consistently organized expert talk series on a wide range of topics in and around mathematics. Mathematics, at its heart, is a discipline that values clarity of thought, patience, and imagination. Today's occasion gains special significance as we celebrate the 138th birth anniversary of Sri Srinivasa Ramanujan, an Indian mathematician whose extraordinary brilliance still continues to inspire mathematicians even after a century. Therefore, National Mathematics Day is not just a celebration of a great mathematician, but a celebration of the spirit of inquiry, the courage to explore patterns, to ask profound questions, and to pursue ideas with quiet dedication. So today, we have with us our chief guest, Professor Robin Wilson, Emeritus Professor from Open University UK in Gresham College, London. He is going to speak about Euler's pioneering equation, the most beautiful theorem in mathematics. We are so happy to have you here today. Thank you, sir, for joining for this talk. Now, let me welcome Vinod, sir, to share a few words.
Thank you, Amrita. Dear participants, National Mathematics Day greetings to all. Today, this auspicious day of 138th birth anniversary of the great Indian mathematical legend Srinivasa Ramanujan, we are celebrating this day with the 16th webinar of Math Ecstasy Series. We are really blessed to have Professor Robin Wilson, Emeritus Professor, Open University UK and Gresham College, London, to deliver today's invited talk. I am deeply indebted to you, sir, for accepting our invitation and joining with us.
Thank you.
I also would like to express my gratitude to Professor 𝕤𝕤𝕤𝕤, Cochin University of Science and Technology, for his support throughout the journey of Maths Aspirants. I also would like to express my gratitude to all members of the organizing team and the entire community of Maths Aspirants. I'm sure that the coming hour will be a great mathematical feast for all those who gathered here. I welcome everyone to this event. Thank you.
Thank you, sir. Now, let me welcome Ms. Rosna. She's a postdoc fellow at Fern University in Hagen, Germany. She's going to introduce our speaker.
So thank you. So my task is to introduce the speaker. So it's my great pleasure to welcome our speaker for today's webinar. We are honored to have with us the Professor Robin Wilson, Emeritus Professor at the Open University UK and at Gresham College, London. Professor Wilson is an internationally respected mathematician and historian of mathematics with over 50 books to his credit, spanning topics from graph theory and history of mathematics to recreational puzzles and even the mathematics of music. His research has focused on graph colorings and the famous four-color theorem, and he is widely recognized for his outstanding contributions to mathematical outreach, having delivered more than 1,000 public lectures worldwide. Today, he will guide us through one of the most elegant results in all of mathematics, Euler's pioneering equation, often hailed as the most beautiful theorem ever discovered. I would like to invite Professor Robin Wilson for the talk, and we are looking forward for the talk. Please, sir.
I'm now sharing my screen. So I'd like to thank you very much for inviting me to give this talk today, in which I'd like to tell you about Euler's pioneering equation, often called the most beautiful theorem in mathematics. One person who features throughout my story is the 18th century Swiss mathematician Leonhard Euler, who spent most of his life in the imperial courts of St. Petersburg in Russia and in Berlin. The most prolific mathematician of all time, Euler published over 800 works in over 70 volumes, ranging across almost all branches of the mathematics and physics of his time. Indeed, much of modern mathematics and physics can be traced back to him. Why is it the most beautiful theorem in mathematics? The description comes from when Euler's equation topped a poll run by an American mathematics magazine. But such polls aren't restricted to mathematicians. A similar poll for the greatest equation ever was taken by Physics World, with Euler's equation appearing in the top 2, way ahead of such equations as Einstein's E=mc² and Newton's laws of motion. Other people have been equally impressed. Indeed, when only 14, the future Nobel Prize-winning physicist Richard Feynman called Euler's equation the most remarkable formula in math, while Fields Medal winner Sir Michael Atiyah described it as the mathematical equivalent of Hamlet's "to be or not to be" from Shakespeare. Very succinct, but at the same time very deep. And the mathematical popularizer Keith Devlin was even more eloquent, saying, like a Shakespearean sonnet that captures the very essence of love, or a painting that brings out the beauty of the human form that is far more than skin deep, Euler's equation reaches down into the very depth of existence. It is even featured in 2 episodes of The Simpsons. So what is this most beautiful theorem in mathematics? And what is the greatest equation ever? Euler's equation is important because it combines 5 of the most important constants in mathematics. 1, the basis of our counting system. 0, the number that expresses nothingness. Pi, the basis of circle measurement. E, the number linked to exponential growth. And I, an imaginary number, the square root of -1. And it also involves the fundamental mathematical operations of addition, multiplication, and taking powers. So if we take the number e and raise it to the power I times pi, and then add 1, we get 0. Or equivalently, e to the I pi equals -1. And as one participant in the Physics World poll remarked, what could be more mystical than an imaginary number interacting with real numbers to produce nothing? And it even appeared on this Chinese postage stamp issued earlier this year. I'll now introduce these 5 constants one at a time, giving their history, before showing how they combine to give rise to what we've called Euler's equation. So we'll start with 1, the basis of our counting system. But how do we count? We use a decimal system using only the 10 digits 1 to 9 and 0. But it's also a place value system because the placing of each number determines its value. For example, the number 5157 means 5,100, 5 tens and 7 ones, or 5 times 10 cubed, plus 1 times 10 squared, plus 5 times 10 to the 1, plus 7. So here the numeral 5 plays 2 different roles depending on its position. There's 5,000s and as 5 tens. And the advantage of such a place value system is that we can then carry out our number calculations column by column. Another example is the binary system used in computing, which is based on 2 rather than 10. So a binary number such as 1101 means 1 lot of 2 cubed plus 1 lot of 2 squared plus no lots of 2 to the 1 plus 1 unit, corresponding to our decimal number 13. So how did our counting systems arise? How did early civilizations count? Let's look at a few. Around 1800 BC, the Egyptians, who wrote on papyrus, used a decimal system, but it wasn't a place value system because they used different symbols for 1, a rod, 10, a heel bone, 100, this coiled rope, and so on, repeating them as often as necessary. So the number below, reading from right to left, is 2 lotus flowers, 6 coiled ropes, 5 heel bones, and 8 rods, or 2,658. And around the same time, the Mesopotamians, or Babylonians, were imprinting their numbers on clay tablets. They used a place value system, but it was based on 60, not on 10. A method of counting we still use when we measure time, 60 seconds in a minute and 60 minutes in an hour. With a vertical symbol for 1 and a horizontal one for 10, the number 11237 shown here means 1 lot of 60 squared plus 12 lots of 60 plus 37 units, which add up to our decimal number 4,357. Moving forward by over 1,000 years takes us to classical Greece and Rome. We're all familiar with Roman numerals, a decimal system with letters representing numbers. But it's not a place value system because different letters are used for 1, 10, 100, and 1,000, and for 5, 50, and 500. Because calculating with these letters is awkward, they used a counting board or abacus for their everyday calculations. The Greek system below seems even more confusing. It's also a decimal system, but again, it's not a place value system because different Greek letters represent the units from 1 to 9, the 10s from 10 to 90, and the hundreds from 100 to 900. So a number like 888 would be written as 800 plus 80 plus 8, or omega pi eta. In China, they used counting boards for their arithmetic, placing small bamboo rods into separate compartments for units, tens, hundreds, and so on. This was a decimal place value system, one of the earliest. Here, each number came in 2 forms, vertical above and horizontal, which alternate. So 1,713 is a horizontal 1, a vertical 7, another horizontal 1, and a vertical 3. You see they're alternating. Whereas for the number 6,036, the 0 gives us an empty box, and the 2 forms of 6 are different. A different method of counting was used for the calendar calculations of the Mayans of Mexico and Central America. These survive in a small number of codices drawn on tree bark and then folded. Here, counting was based mainly on 20, combining dots and lines to give all the numbers from 1 to 19, as shown here. For larger numbers, they then piled these numbers on top of each other. So here you can see 12 20s in red, plus 13 in black, corresponding to our decimal number 253. And an attractive feature of Mayan counting was that each number also had a pictorial head form like the ones below. They also had a symbol for 0, the shell-like symbol at the bottom. In India, there was a base 10 system. Around the year 250 BC, the edicts of King Asoka, the first Buddhist monarch, were carved on pillars around the kingdom. Some of these contained early examples of Indian numerals, as a decimal place value system began to emerge, using only the numbers 1 to 9 and later 0. So this brings us to our second number, 0. But how did it arise? We've seen how the Chinese left spaces in their counting boards, while other civilizations left spaces in the sand to distinguish between numbers like 35 and 305. But gradually special symbols began to emerge. Here's a cave in Gwalior, where 270 is clearly seen on the wall. But there was great excitement a few years ago when some birch bark that had lain undiscovered for over 100 years was found in the Bodleian Library in Oxford. This had dozens of blobs on it, all representing 0, and predates all other known appearances of 0 by some 400 years. So note that 0 can play two roles. As a placeholder, as we've seen, but it's also a number we can calculate with. Positive and negative numbers were already used in money markets for profits and debts. And around the year 600, rules for calculating with them, and with 0, called cipher or naught, were given by the Indian mathematician Brahmagupta. Here are some examples. The sum of 0 and a negative number gives a negative number. Below, a negative number taken from 0 becomes positive, and so on. The only meaningless rule here was the last one, relating to division by 0, and saying that 0 over 0 is 0. But dividing by 0 is forbidden, because if we cancel the zeros in an equation like 4 times 0 equals 9 times 0 on the left, we get 4 equals 9, which is nonsense. So you cannot divide by 0. The diagram here shows how our number system developed over the centuries, from India, via the Middle East to Europe, leading to the numerals at the bottom, which we can clearly recognize. And also developing were the Arabic numerals on the right, which are still used in Middle Eastern countries. But it took many centuries for what we now call the Hindu-Arabic numerals to become fully established. Here on the left is a 16th century picture representing arithmetic, and contrasting the modern algorist with his Hindu-Arabic numerals, with the old-fashioned abacist with his counting board. Meanwhile, arithmetic books promoting the Hindu-Arabic numerals began to appear. By Fibonacci in 1202, Luca Pacioli in 1494, and Robert Record in 1543. And the drawing on the right, which comes from Pacioli's book, shows us how to calculate on one's fingers. Let's now turn to our third number, pi, which arises in two ways. It is the ratio of the circumference of a circle to its diameter. Pi equals c over d, so c equals pi d, or 2 pi r, where r is the radius. And this ratio of pi is the same for circles of any size, from a pizza to the moon. And pi is also the ratio of the area of a circle to the square of its radius. Pi equals a over r squared, so a equals pi r squared. And again, this ratio is the same for all circles, as proved by Euclid in the 3rd century BC. And here you can see another Chinese stamp, this time featuring pi. Now, we can never write down pi exactly. Its decimal expansion goes on forever. But if my form of 5 decimal places weren't enough for you, here are some more. But we can never write out pi in full. It's what we call an irrational number. And although it has now been calculated to over 100 trillion decimal places, there's still a long way to go. So when did people start to measure circles? Several early civilizations needed an estimate for their circumference or area. And even though they had no conception of pi as a number, their results yielded good approximations to it. For example, there's a Mesopotamian clay tablet which gives the ratio of the perimeter of a regular hexagon to the circumference of the surrounding circle. And it gives the ratio as a sexagesimal number 0.5736. Now, if the radius is r, then each side of the hexagon is also r, because these are equilateral triangles. And so this ratio is 6r over 2 pi r, or 3 over pi, and equals 57 over 60 and 36 over 3600. And if you calculate it, this gives us pi is 3 1/8, or 3.125 in decimals. A lower estimate for pi that's within 1% of its true value almost 4,000 years ago. Around the same time, an Egyptian papyrus asked the following question. Given a round field of diameter 9 ket, that's the unit, what is its area? The answer is given in steps. Take away 1/9 of the diameter, which is 1, leaving 8. Then multiply 8 times 8 to give 64 setat of land as the area. So to find the area, they reduced the diameter by 1/9 and then squared the result. And this method was probably found by experience. In terms of the radius, the area turns out to be 256 over 81 times r squared, so that pi is about 256 over 81, or 3.160. An upper estimate was also within 1% of its true value. But a better method for finding pi was introduced by the Greeks and would be used for almost 2,000 years. Often credited to Archimedes, it dates back to the 5th century BC, when the Greek sophists Antiphon and Brighton approximated a circle by regular polygons and attempted to obtain better and better estimates for the area by repeatedly doubling the size until the polygons eventually became the circle. 200 years later, Archimedes adopted the same idea, but worked with perimeters rather than areas. Starting, as you see here, with hexagons inside and outside the circle, he obtained the lower estimate of 3 and the upper estimate of 2 root 3, or about 3.464. Not very good estimates. But doubling the number of sides to 12 gave the better estimates of 3.106 and 3.215. 3 further doublings, up to polygons with 96 sides, eventually gave him bounds for pi of 3 and 10 over 71, and 3 and 1 over 7, or 22 over 7. And this gives us pi to 2 decimal places. What was happening elsewhere? In China, around the year AD 263, 𝕼𝕤 also used polygons to approximate pi. Starting again from hexagons and dodecagons, he found simple methods for calculating the successive areas and perimeters when he doubled the number of sides. And for polygons with 192 sides, he again obtained bounds of about 3.14. 4 more doublings then led him to polygons with 3072 sides and to pi equals 3.14159, 5 decimal places. Even more impressively, around the year 500, Zhu Zhongzhi and his son doubled the number of sides 3 more times to more than 24,000 and obtained pi to 6 decimal places, as shown here. They also improved Archimedes' fractional value of 22/7 to 355/113, which also gives pi to 6 decimal places. And this improved fraction wasn't rediscovered in Europe for another 1,000 years. After this, everyone got in on the game as the number of sides continued to double with corresponding increases in accuracy, leading eventually to the remarkable Ludolf van Keulen, who used polygons with over 500 billion sides to give pi to 20 decimal places. But not content with this, he then used polygons with 2 to the power 62 sides to find pi to 35 decimal places, as shown here. As he asked for this latter value to appear on his limestone, to appear on his tombstone in Leiden, in the Netherlands, and for many years pi was known in Germany as the Ludolfian number. Now, before proceeding, I'll need to introduce another way of measuring angles, instead of our usual rather arbitrary values based on 360 degrees. Why 360? This method was introduced by Roger Coates, a colleague of Isaac Newton. If we take a circle of radius r and mark out a distance of r on the circumference, then the angle it creates at the center is about 57 degrees, and we call it 1 radian. And more generally, for any angle, the number of radians is the ratio of the length of the circular arc to the radius r. So an angle of 180 degrees, which corresponds to a semicircular arc with length pi r, is then pi radians. So here you can see a table of degrees and ratios. So 45 degrees is pi over 4 radians, and 30 degrees is pi over 6 radians. Returning now to estimating pi, a new and highly productive method, which was used extensively throughout the 18th and 19th centuries, involved the inverse tangent function, usually written as tan to the minus 1x or as arc tan x. This next bit will get a little technical, but do hang in here. It won't last long. But in particular, I'll be using radian measure for angles. So y is equal to tan x. X is equal to tan to the minus 1y. It's the inverse. For example, tan of pi over 4 radians, that's tan 45 degrees, is 1. So tan to the minus 1 of 1 is pi over 4. And tan pi over 6 radians, that's tan of 30 degrees, is 1 over root 3. So tan to the minus 1 of 1 over root 3 is pi over 6. And we can combine different values of tan to the minus 1 using the formula shown here. Tan to the minus 1 of a plus tan to the minus 1b is tan to the minus 1 of a plus b over 1 minus ab. So for example, when a is 1/2 and b is 1/3, we get tan to the minus 1 of 1/2 plus 1/3 over 1 minus 1/6, which is just tan to the minus 1 of 1, which is pi over 4. Now, many important mathematical functions can be written as infinite series. For example, tan to the minus 1 of x is the infinite series shown here, with only odd powers of x, x cubed, x squared, and so on, and with odd numbers as denominators. This result was already known in 15th century India, but is usually named after the Scotsman James Gregory, shown here, who rediscovered it 300 years later. If we now put x equals 1, we get a series expression for pi over 4, a result also known earlier in India, but often credited to Leibniz. This is one of the most remarkable results in the whole of mathematics. By simply adding and subtracting numbers of the form 1 over n, we get a result involving the circle number pi. But unfortunately, this series converges so slowly that we cannot use it to find pi in practice. For example, the first 300 terms of the series give pi to only 2 decimal places, while the first 500,000 terms give us only 5 places. But we can use Gregory's series to estimate pi if we substitute values other than 1. Remember that 10 to the minus 1/2 and 10 to the minus 1/3 add up to pi over 4. So we can substitute x equals 1/2 and x equals 1/3 into the series for 10 to the minus 1x, giving us the 2 series here. And because of the increasing powers of 2 and 3 in the denominators, these converge much faster, yielding good estimates for pi. Indeed, 200 years later, this very same result was used to find pi to 261 decimal places. Are there other 10 to the minus 1 results where the series converge even faster? In 1706, the Englishman John Machin, shown here, repeatedly used the 10 to the minus 1 addition formula to get this formula for pi. And he then wrote out the 2 10 to the minus 1x series shown here, involving powers of 1/5 and powers of 1 over 239. But these series converge rapidly because of the powers of 5 and 239 in the denominators. And also 5 is an easy number to divide by, and Machin was able to calculate pi by hand to 100 decimal places, a great improvement on anything that had been done before. Indeed, 1706 was a good year for pi. As well as Machin's result, a Welsh maths teacher called William Jones wrote a mathematics text in which he introduced for the first time the symbol pi for the circle number. So here are 2 extracts from his book. Above, you can see Machin's series with the 5s and 239s, followed by the first ever appearance of pi. And below is Machin's value for pi in full, written out in full and just true to above 100 places. It's computed by the accurate and ready pen of the truly ingenious Mr. John Machin. This and similar results can be used to obtain improved values for pi. And the most notorious of these was obtained by William Shanks, who in 1873 used Machin's formula to calculate pi to an impressive 707 decimal places. And these were later inscribed in a ceiling frieze in the pi room of the Palace of Discovery in Paris, where they can still be seen. But unfortunately for him, and for the palace, it was later found that only the first 527 of these decimal places are correct. But they obviously didn't want to repaint the ceiling. A rather different way to approach pi took the form of an experiment, and was due to the French mathematician and naturalist Nicolas de Buffon. Suppose you throw a large number of needles or matchsticks of length L onto a grid of parallel lines at a distance of d apart, and record the proportion of the needles that cross a line. It can then be proved that this proportion is 2 over pi times L over d, from which we can calculate a value for pi. So here, for example, L over D is 4 over 5, and exactly 5 of these 10 needles cross lines. So 2 over pi times 4 over 5 equals 5 over 10. And this gives us pi equals 3.2, which isn't too bad a result for only 10 needles. I'll end my discussion of pi with a simple puzzle that appeared in the early 18th century. If you haven't seen it before, you may find its answer surprising. The circumference of the Earth is about 40,000 kilometers. Assuming the Earth to be a perfect sphere, suppose we tie a piece of string of this great length tightly around the equator. We then extend the string by just over 6 meters and prop it up equally all around the Earth. How high above the ground is the propped up string? So you've taken the string, you've tied it around the Earth, you've added 2 meters, and you prop it up and all around the Earth. What's the gap? Most people think the resulting gap must be extremely small, perhaps a tiny fraction of a millimeter. But the answer is a whole meter. And in fact, we get the same answer whether we tie the string around the Earth, a tennis ball, or any other sphere. Because if the sphere has radius r meters, then the original string has length 2 pi r. When we extend it by 2 pi meters, the new circumference is 2 pi r plus 2 pi, which is 2 pi times r plus 1. So the new radius is r plus 1, 1 meter more than before. Let's now move on to our fourth number, the exponential number e equals 2.71828, etc. Here we're concerned with how quickly things grow. We use the phrase exponential growth to indicate something that grows very fast. But how fast is this? Well, we note first that like pi, the decimal expansion of e goes on forever. The symbol e first appeared in print in 1736. Euler had used it in an unpublished paper of 1737 and in a letter of 1731, but it first appeared in print in 1736 in his book Mechanica, a book on the mathematics of motion. And here it is in the penultimate line where e denotes the number whose hyperbolic logarithm is 1. So that's the first appearance in print of e for exponential. Well, to illustrate what we mean by exponential growth, here's a story about the invention of the game of chess. The wealthy king of a certain country was so impressed by this new game that he offered the wise man who invented it any reward he wished. To which the wise man replied, "My prize is for you to give me 1 grain of wheat for the first square of the chessboard, 2 grains for the second square, 4 grains for the third square, and so on, doubling the number of grains on each successive square until the chessboard is filled." The king was amazed to be asked for such a tiny reward, or so he believed, until his treasurers calculated the total number of grains of wheat. This is 1 plus 2 plus 2 squared and so on, and it works out at 2 to the power 64 minus 1 grains, which is enough wheat to form a pile the size of Mount Everest. And if you placed the grains end to end, they would reach the nearest star, Alpha Centauri, and back again. Let's see how quickly other sequences can grow. A very simple form of growth is linear growth, as in the counting numbers n equals 1, 2, 3, 4, 5, and so on. Somewhat faster is the way the perfect squares n squared grow, and even quicker is that of the cubes n cubed. These are all examples of polynomial growth because they involve powers of n. But alternatively, we could look at powers of 2 or of any other number. As we saw in the chessboard story, the numbers 2 to the n, the powers of 2, start slowly, but soon gather pace because each successive term is twice the previous one. And the powers of 3 grow even more quickly. These are examples of exponential growth where n appears as the exponent. To compare these types of growth, let's calculate the running times of some polynomials and exponentials when n is 10, 30, and 50 for a computer doing 1 million operations per second. For polynomial growth, such as n cubed, such a computer would take about 1/8 of a second when n is 50. But exponential growth, such as 2 to the n, is much greater, as we've seen. When n is 50, the computer would take over 35 years and would be vastly longer than this for 3 to the power n. So in the long run, exponential growth tends to exceed polynomial growth, often by a huge margin. Algorithms that run in polynomial time are generally thought to be efficient, whereas those that run in exponential time normally take much longer to implement and are regarded as inefficient. Now, returning to E, what exactly is this number and how did it arise? In 1683, the Swiss mathematician Jacob Bernoulli was calculating compound interest. Given a sum of money to invest at a given rate of interest, how does it grow? The answer depends on how often we calculate the interest. How much is earned if we calculate the interest yearly, or twice a year, or every month, or every week, or every day, or continuously? As an example, to keep the calculation simple, let's see what happens if we invest £1 at the unlikely annual rate of 100%. After 1 year, our £1 has doubled to £2. But if we calculate the interest twice a year by 50% each time, then after 6 months, our £1 is multiplied by 1.5 to give £1.50. And after another 6 months, that amount is multiplied by another 1.5 to give £2.25, which is more than before. Please excuse me for using English currency. Now let's calculate the interest every 3 months. Here there are 4 periods, and after each one, the amount is multiplied by 1.25. First to £1.25, then to about £1.56, then to £1.95, and by the year to about £2.44, which is £1 times 1.25 to the power 4. So the final amount is larger still. And as the periods get shorter, what happens? Do the final amounts increase without bound, or do they settle down to a limiting value? The results are shown here to 5 decimal places. And to find them, note that if the year is divided into n periods, then after each period, the amount is multiplied by 1 plus 1 over n, so that the final amount is 1 plus 1 over n to the n. So here you can see a table. For a year, it's £2. For every half year is 2.25, and the numbers are moving, and they are tending to a limit. So as n increases, the final amounts approach a limiting value that corresponds to when the interest is calculated continuously. And as you can see, this limiting amount of about 2.71828 is our exponential number E. So that's how E arose. And the greatest advances in understanding exponentials were made in the early 18th century. After Bernoulli, the main figure in this story was Euler, who investigated the number E and the related exponential function e to the x. And in 1748, his Introduction to the Analysis of Infinites, one of the most important books in mathematics ever written, brought together many of his results from earlier works. So let's look at some of his main findings. We've just seen that E is the limit of the numbers 1 plus 1 over n to the power n as n increases indefinitely. And similarly, we can show that e to the x is the limit of 1 plus x to the n, 1 plus x over n to the n for any number x. But as Isaac Newton had already discovered, E is also the sum of the infinite series shown here. The denominators are the factorials. 1 factorial, 1 plus 2, 1 times 2, 1 times 2 times 3, and so on. And more generally, there's a similar series for e to the x, which converges for all values of x. On the right is the graph of y equals e to the x, where an important feature is that at each point x, the slope of the graph is also e to the x. That is, the slope at any point is the y value. So the curve becomes steeper and steeper as x increases. So let's end our discussion of exponentials by returning to exponential growth. In 1798, Thomas Malthus wrote his famous essay on population, where he contrasted the steady linear growth of food supplies with the exponential growth in population. He concluded that, however one may cope in the short term, exponential growth would win in the long term, and there would be severe food shortages, a conclusion that was sadly borne out in practice. How fast does a population grow? If n of t is the size of a population at time t, and if the population grows at a fixed rate k proportional to its size, then we have the differential equation dn by dt equals k times n. And this can be solved to give n of t is n0 e to the power kt, where n0 is the initial population. Clearly an example of exponential growth. And in the same way, we can model exponential decay, as for example, for the decay of radium or the cooling of a cup of tea. We come now to the last of our 5 constants, the imaginary square root of -1. This can be traced back to the 16th century, where Cardano, the Italian mathematician who wrote about cubic equations, was trying to solve a number puzzle. Divide 10 in 2 parts whose product is 40. To do so, he let the 2 numbers be x and 10 minus x. So that x times 10 minus x is 40, or x squared minus 10x plus 40 equals 0. Solving this quadratic equation, he found the solutions to be 5 plus the square root of -15 and 5 minus the square root of -15, which seemed meaningless. Commenting that, nevertheless, we will operate, putting aside the mental tortures involved, he checked the answers worked. If you add these, you get 10, and if you multiply them, you get 40. But he complained that so progresses arithmetic subtlety, the end of which is as refined as it is useless. So he solved the problem, but the answers were things that he didn't understand. And in fact, trying to take the square root of a negative number doesn't seem to make sense. After all, 1 times 1 is 1, and -1 times -1 is also 1. As the Victorian mathematician Augustus de Morgan remarked 300 years later, we have shown the square root of -80 to be void of meaning, or rather self-contradictory and absurd. while his contemporary, the astronomer George Airy, commented, "I have not the smallest confidence in any result which is essentially obtained by the use of imaginary symbols." However, Leibniz was more encouraging, claiming that the imaginary numbers are a wonderful flight of God's spirit. They are almost an amphibian between being and not being. To Euler's shame, even he, who had used them so effectively, criticized them. Now, for many purposes, our ordinary real numbers are enough. But suppose we now agree to allow this mysterious object called the square root of -1, or I, as Euler named it. We can then form many more numbers, such as 1 plus 3i and 2 plus I. Ignoring for the moment what these actually mean, we can then carry out some simple calculations of them. Adding is straightforward. We just add the bits without I, that's A and C, and then the bits with I, that's the BI and DI. And multiplying is also straightforward, as long as we remember to replace I squared whenever it appears by -1. Now I've given an example at the bottom. We have 1 times 2. We have 3i times I, which is -3, and so on. Now we can also represent these numbers geometrically. This was first done by Caspar Wessel of Norway, and later by Carl Gauss and Jean-Robert Argand of France. It's often called the Gaussian plane or the Argand or Argand's diagram, but neither name is historically correct. So it's much better to call it the complex plane. And here we represent each complex number, a plus bi, by the point with coordinates AB. So the picture on the left shows 4 points, such as 1 plus 2i and 3 plus I. We can then add two complex numbers by using the parallelogram rule as shown on the right. So as before, 1 plus 3i plus 2 plus I is 3 plus 4i. Now, as you've seen, there was much suspicion in Victorian times about these imaginary numbers. The Irish mathematician and astronomer William Rowan Hamilton largely ended this suspicion by defining the complex numbers a plus bi as pairs AB of real numbers, which combine to the particular rules shown here. So since complex numbers can be represented in the plane, a natural question is, can we extend the idea to 3 dimensions with numbers of the form a plus bi plus cj, where I squared and j squared are both -1. Addition is still okay, but multiplication is not, because of the product I times j that arises when you try. Hamilton tried many ways to deal with this. He put I times j equals 1, I times j equals 0, and so on, but everything failed. As he later wrote to his son Archibald, "Every morning on my coming down for breakfast, your brother William Edwin and yourself used to ask me, 'Well, Papa, can you multiply triplets?' Whereto I was always obliged to reply with a sad shake of the head, 'No, I can only add and subtract them.'" And indeed, after struggling with these troublesome triplets for many years, Hamlet had his moment of glory on the 16th of October 1843 during a walk with his wife along Dublin's Royal Canal, when, as he put it, an electric current seemed to close and a spark splashed forth. I pulled out on the spot a pocketbook and made an entry there and then. Nor could I resist the impulse to cut with a knife on a stone on Broome Bridge as we passed it, the fundamental formula with the symbols I, j, and k, namely I squared equals j squared equals k squared equals ijk equals -1. So these are the quaternions with 4 terms, not 3, but 4 terms, a plus bi plus cj plus dk. Here, I squared, j squared, and k squared are all -1, but multiplication is no longer commutative. That means that ij is not ji, it's minus ji. Jk is not kj, but minus kj. And ki is not ik, but minus ik. This works. You can then multiply any 2 quaternions as long as you stick to these rules. Well, now we've got our 5 constants, let's return to Euler's equation. And as we'll see, Euler's equation is a special case of a more general result that he published in 1748. This fundamental result, sometimes called Euler's identity, relates the exponential function e to the x to the trigonometrical functions cos x and sin x. But how can the function e to the x, which goes shooting off to infinity as x becomes large, have anything to do with cosine and sine, which forever oscillate between the values 1 and -1? There's certainly no real reason for such a connection, but there is a complex reason. Introducing the complex number I leads to the result shown here. And discovering this was one of Euler's greatest achievements. And as he himself commented, from these equations, we can understand how complex exponentials can be expressed by real sines and cosines. It's one of the most remarkable equations in the whole of mathematics, beautifully connecting these seemingly unrelated functions. The result has even appeared on a Swiss postage stamp, where it appears up the left-hand side. And incidentally, although Euler's results may seem rather abstract, they are of fundamental importance to physicists and engineers. This is because exponentials of the form e to the kt describe things that grow if k is positive, or decay if k is negative. Well, those of the form e to the ikt describe circular motion. But by Euler's identity, e to the ikt is made up from cos kt and sin kt, and can therefore be used to represent things that oscillate. For example, e to the 𝑖𝜔t refers to an alternating electric current with angular frequency omega. And mathematically, these imaginary exponentials are much easier to deal with than cosines and sines. And indeed, for more advanced topics, such as quantum mechanics and image processing, many calculations cannot be carried out without them. Well, I won't prove Euler's identity. It uses infinite series, the infinite series for exponential, cosine, and sine. But here you can see how we can deduce Euler's equation from it. We simply let x equals pi, the radian form of 180 degrees. And because cos pi is cos 180 degrees, which is -1, and sine pi is a sine of 180 degrees, which is 0, you get e to the I pi equals -1 plus 0i equals -1. So e to the I pi plus 1 equals 0, as we wanted. But should Euler be credited with this equation, e to the I pi plus 1 equals 0? Surprisingly, he never seems to have written it down explicitly, although he surely realized that it does follow directly from his identity e to the x equals cos x plus I sin x, as I've just shown. Other mathematicians obtained similar results, but like Euler, never stated it explicitly. And in fact, we don't know who first did so, although there's an early appearance of it around the year 1813. But almost everybody now attributes the result to Leonhard Euler, So we surely justified in naming it Euler's equation to honor the achievements of this truly great mathematical pioneer, a word that describes him so well and which appropriately includes among its letters our 5 constants pi, I, 0, 1, and E. And if you want to read more about this, I can obviously recommend this wonderful paperback on the left, as well as the other Euler books shown here. So many thanks for listening.
Thank you, sir.
Hi, it was a very nice talk.
Thank you
And
very much.
actually, I'm really happy because my serious study in graph theory, I started with your book, Introduction to Graph Theory. So very nice to see you.
I've done lots of books on graph theory.
Thank
So
you.
there's 2 types of me. Well, one of me is the graph theorist, and the other part of me is a historian of mathematics. And I've also written books on the history of graph theory.
Yes, yes. Yeah, my query is regarding recently, maybe in 2024, it was known that 2 Indian physicists, they are working in string theory.
Right.
One Anil Saha and Vishwajit Saha, they
Right.
introduced a new series representation for pi, which involve a variable parameter, so that will offer a number of series, each converging to pi. I think that
Oh,
work was not published. They are from IISc, Indian Institute of Sciences. So anything about it, you know, sir?
I wasn't aware of that. There are several series, of course, which give rise to pi. There's a famous one about if you add the squares of reciprocals, 1 plus a half squared plus a third squared plus a quarter squared. This is known as the Basel problem, and everyone knew it was about 1.6, but they couldn't find the exact answer, which is pi squared over 6. And like the other one, it's amazing that these things which seem to have nothing to do with pi appears. There are lots of other results on pi, incidentally. Thank you for telling me about the new series. Of course, there are also lots of other results. Some very famous series, of course, were due to Ramanujan, who came up with some absolutely incredible series involving pi and involving all sorts of very, very strange numbers that you just wouldn't, like 1601 and other things that you just wouldn't expect to see. So if you're interested in series for pi, you should certainly go and look up Ramanujan's work and some of the remarkable results that he obtained.
Okay, so thank you, sir.
Thank you for your question.
Thank you so much.
Hello, sir. Good evening.
Hello.
I'm Veena Mathad from Mysore, India.
Yes.
You have mentioned some books at the end of your lecture, sir. Very nice books they are. Recently, Professor H.B. Walikar of Karnataka University, Dharwad, he has also written one book titled God's Own Equation. He has referred to this equation e power pi I pi plus 1 equal to 0 as God's own equation, and he has written a very beautiful book on that also.
All right. Yes, I mean, several people have written books on Euler's equation. I mean, mine is obviously one, but there are certainly I knew a couple. So he tried. I wasn't aware of the new one.
Yeah, it's new one. It's published in 2017.
Oh right. Oh, okay.
Yeah.
Oh, I'm sorry, I didn't know about it. Otherwise, I couldn't.
He has mentioned it as the God's own equation.
God's own, okay, yes.
God's own equation, yeah. Because of its beauty and mystery, he has mentioned, he has given the title as God's own equation for this book, sir.
Well, I mean, if any equation is to be called that, it's certainly that's certainly the one that ought to be from a mathematician's point of view.
Yeah.
If I can be rather naughty and advertise another book of mine which came out this year, it's called Some Stories. It's SUM, that's a pun, of course, and this is about the origins of equations, of which the one we've been talking about today is only one example. So, for example, it's 18 different essays about equations starting with 1 + 1 = 2, introducing the counting numbers, and it's got a chapter on pi, it's got a chapter on E and so on, and it's got all of these different chapters. So each chapter talks about equations and how they arose historically, much as I did today. And you may be interested, I've actually started preparing some films for high schools. One film, each film is about 15 or 20 minutes, and is aimed at high schools. These films are becoming available. 4 of them are already around, and I've filmed another 5. If you go to the Oxford Mathematics, Oxford Mathematical Institute, you should find them there. Because so if you've got school children who want to know about some of these things, get them to look at the films. They're about 15 minutes each, and I think they'll find them quite interesting.
Yes, sir. Yes, sir. Thank you, sir. Thank you.
But apologize for advertising my own book again.
Sure, sir.
Yeah. Someone's come up with a comment about a result that Hardy mentioned. Was that on in the chat? Okay, we'll come back to that.
Hi, sir. This is Ram Kumar. Hi, sir. Can you hear me?
Yes, I can hear you.
Yeah, sir. It was an excellent talk, sir. Thank you very much, for making it up. I've got 2 questions for you. One on a lighter note. I saw it in Wikipedia that you are the son of former British Prime Minister. So
That's right.
you have chosen the field of mathematics, not politics. So if you can share a few views about it, we'll be happy to know about it. And one more thing. When we teach complex numbers, regarding imaginary numbers, since we don't use them in real life, how do we tell students that these numbers are usually used in higher mathematics, but we don't use them in real life, right? So how do we explain students, say for example school students, to be able to understand complex numbers related to the value of I more easily? Thank you so much, sir.
Okay, for the first question, I mean, I've always wanted to be a teacher. Most of our family were teachers, actually, and my father was taught at Oxford University for a short while. But I've always been keen on mathematics, and I've always wanted to teach. And ever since I was about 11, I think I wanted to be a mathematics teacher, and that's what I have become. As far as telling people about I, it's very, very difficult because because it is counterintuitive. These numbers don't seem to exist. Possibly these things like 𝔼𝕦𝕝𝕤𝕤𝕤. You say it's not just pure mathematics it comes in. It comes everywhere in applied mathematics, and as I explained before, it comes very much into all sorts of different branches of physics. And it may be that sort of things like circular motion and everything like that, and electrical currents and things, the way I mentioned earlier, might be the best way of trying to persuade them that complex numbers have some sense. Because, as I say, well, you can regard it 2 ways. If you want to regard it as pure mathematics, it's a game you play. You've got the rules, and you just play your game. But that won't convince a lot of school children. So perhaps the more applied way is better. Of course, electrical engineers don't use the letter I, they use the letter J, because they already use I for current. So you'd have to explain that. But basically, I mean, I haven't got experience of teaching it to the school children, but I would think some of these electrical engineering examples might be a way in.
Thank you, Professor. Thank you.
Hello, sir.
Hello.
I'm Saloni. I'm just post-graduated from
Yep.
𝕼𝕤𝕤𝕤 Pune Pune University and struggling to get admission in for the PhD. So I'm just a student. But actually, I have a question regarding in respect to the graph theory. Please try to understand because I'm not so much expressible. Suppose that I have one system in which a few things goes parallelly and the other things are dependent on each other. Without executing the one, the other can't be executed. And the time is the average time we have. Now I want to optimize the system so that in the minimum time, I can go through the that system. So how I can apply the graph theory over here? What I have thought is to use the directed graph and then use the other algorithms, but I'm not very pretty sure that whether this will work or not. So I want the answer of this.
I'm afraid I'm not going to be any help. I mean, I haven't come across that particular example, and I mean, as you know, graphs and directed graphs in particular are used widely in all sorts of applications. But I'm afraid I'm not familiar with that one, and I don't think there's anything I can do to help you. But anyway, all power to your elbow. Looking at applications, I'm very much a pure graph theorist, mainly involved with colouring problems and things like that. So I'm afraid I haven't actually looked so much at your area. So apologies.
Okay. Thank you.
Sorry to let you down.
Good evening, sir.
It's okay.
Hello.
Hello.
Am I audible?
Hello. Yes, I can see you. Yes.
Yeah. Good evening, sir. It was a nice talk. I'm Shikha. I'm a PhD scholar at Indian Institute of Technology, Mandi. And sir, you have talked about complex number, quaternion. So I would like to know that is there any other high dimensional number system? And if there exists such high dimensional number systems, so how do we use them in real life systems?
Okay, so we start with the real numbers, and then we add I, which is I squared, and that gives you the complex numbers, which is 2-dimensional. And then you go on to the quaternions, which is 4-dimensional. Each time you go onto something, you lose something. So when you go to the quaternions, you lose the commutative law. You can no longer multiply things. The next step up is octonions, which is an 8-dimensional thing. They were investigated a lot by Arthur Cayley, an English mathematician. But if you, and so you've got A plus BI plus CJ plus, you've got 8 different terms, and you've got rules which are quite complicated. Well, adding is fine, but multiplying, the rules are quite complicated. But it does give you a definite system. It's no longer commutative, of course, and no longer is it associative. So every time you go up, you double the dimension, you lose another of your favorite laws. So the octonions, so you might Google octonion and find out about them. But you can't go any further. You can go up to 8, but you can't go up any further. You can't go up to 16 or higher. And that was proved at the beginning of the century. I don't know whether it says anything in Euler's pioneering equation about that. Let's have a look. Yes. Oh, if you look in my book, that's the answer to all the world's problems. Octonions, yes. Yeah. So you've got A plus BI plus CJ plus DK and so on. So we've got eight different terms. To multiply them, we actually use a picture called the Fano diagram to do it. But it's all very, very complicated. But you can actually carry it out as a consistent system. But as I say, you've lost commutativity, you've lost associativity, so it's unlikely you can go any further because there are no more laws that you can lose. And this was finally confirmed, it says here, in 1898 by the German mathematician Adolf Hurwitz. So in fact, that's as far as you can go. So quaternions, yes, octonions, yes, but no further.
So, sir, can we use them in real life? It's because it's getting complicated as we are getting higher in dimensions.
Certainly, quaternions have quite widespread use in physics because, of course, if you're dealing with four-dimensional space, meaning the 3 dimensions plus time, if you've got 4 dimensions, then the quaternions have a natural role to play there, and in fact they do. So if you're dealing with, say, the theory of relativity, then the quaternions certainly do come in. They do play a role, and they are actually useful in physics. I don't know whether octonions are used in 8-dimensional physics because I don't know very much about 8-dimensional physics. I suppose in theory they might be, but I would think it's probably quite unlikely. It's just as possible. But if you know anyone that works on 8-dimensional physics, then you could ask them. Probably
So,
not. But certainly quaternions are used in physics, especially in things like the theory of relativity, where you need 4 dimensions to play with.
Okay. So sometimes it happens like we have the results, but we don't actually know the applications of it. Then how to defend in that case? Like we have the results.
Well, to a pure mathematician, it doesn't need to have applications. We just do it for its own interest. And for some of us, it's, I was first a number theorist, actually. I did my PhD in number theory. And what use are prime numbers and all the results in number theory that people discovered over 2,000 years. There were no real practical applications of number theory until fairly recently, when number theory and a result of Euler, my hero Euler, that proves to be absolutely fundamental in cryptography. So number theory is very, very important in cryptography. The security of your credit cards and of the nation's defense all depend on Euler's equation in number theory. So sometimes these bits of pure mathematics do find applications many, many years later. In geometry too, we're all familiar with Euclid's geometry. But then in the 19th century, along comes non-Euclidean geometry, which seemed to have no practical application until some pure maths geometry was done by Riemann in the 1850s. And he did it purely as a mathematical exercise, a bit of pure mathematics with no thought about applications. And yet 50, 60 years later, non-Euclidean geometry and Riemannian's geometry in particular turned out to be absolutely fundamental in the theory of relativity. So the pure mathematicians do it because of its own interest. But hopefully, it's very good if it finds applications. So the pure mathematicians, that's not the direct interest, but obviously in real life or in applications, sometimes bits of pure mathematics will find later on an important application. So both sides can be happy.
Thank you, sir. Nice to have a talk with you.
Thank you.
Good evening, sir. I am Dharmendra Singh from Kasganj, UP and Aligarh also. I recently resigned from BARC Mumbai, and I am preparing for IIT JAM and other exam for integrated PhD and MSc. I want to ask recent research area around Ramanujan work. Can you tell recent research area about Ramanujan work?
Well, I've always been a great fan of Ramanujan, and arguably he is the most intuitive mathematician who ever lived. He seems to have this incredible insight, which when he went to England, he came up with these amazing results. And Hardy said, he'd never seen anything like them before, but he said they must be true because no one would have had the imagination to make them up. And so, as you know, Ramanujan went to England. It was around the beginning of the First World War, and he worked with Hardy, and so he and Ramanujan together tried to prove some of these amazing results that Ramanujan had come up with. One of the particular ones where they worked together and they came out with the spectacular result was a partition number. How many ways can you partition a number? For example, 4 you can write as 4, or as 3 plus 1, or as 2 plus 2, or as 2 plus 1 plus 1. And 5 you can write as 5, and 4 plus 1, and so on. So how many ways are there of partitions of the number 100 or 1,000,000? Is there a formula? A hugely difficult problem. Hardy and Ramanujan worked on this together, and they produced this incredible paper, one of the most amazing papers in the whole of mathematics, where they actually got a formula which very, very complicated. It involved the 24th roots of unity. It involved this amazing function, that amazing function, sort of things which had no right to be there at all, seemingly. But they came up with this result, and again, that's I think it's one of the great results of 20th century mathematics. And Ramanujan came up with so many incredible results particularly involving pi. So, but very, very tragically, as you know, he fell ill and he died at the age of just 32. And one just wonders. Even now, people are still working through notebooks and trying to, prove results or understand how Ramanujan came to think of them. And so even now, 100 years later, people are still still finding his work very, very stimulating to work on. And one thing, just if he hadn't died at 31, but he's had a full life, what mathematics would be like now? I mean, it would be completely different. So it was a great thrill to me when I've had 5 trips to India, and on one occasion I was based in Madurai, and I was driven to Kumbakonam, and I had the great thrill of going into Ramanujan's house and also visiting his school. I didn't have time to go into the temple, unfortunately, but that's one of the most memorable things I've ever done in the history of mathematics, when I was in India, to go to Kumbakonam and see where Ramanujan grew up. It was a fantastic experience. And in fact, a bit later on, they had there was a British radio program called Great Lives, where they contact a famous person and ask them to choose a hero from the past. And on this one occasion, and they have bring in an expert to talk about them. Well, the person they brought in for this was Akram Khan, who was a great Indian choreographer. He designed the choreography for the London Olympics. And his hero was Ramanujan, and I was brought in to talk about Ramanujan on BBC, and what a great man Ramanujan was. So I'm very, very glad that I think when I went to Kumbakonam, they didn't really seem to celebrate him very much. I think they do now. I think he is very much celebrated in his hometown now. But it was a great thrill going there. So I've always been so I mean, 2 of my great heroes in mathematics are Euler and Ramanujan, because they were both just such incredible mathematicians, such intuitive mathematicians, and it's just so sad that Ramanujan didn't live long enough to prove even more fantastic results.
Sir, I'm Shashi Kumar.
Excuse me. 2 more people will be allowed, okay, because of time constraint.
Okay.
One or two at the most. Yeah. Okay.
So long.
Hello. Since you are talking about, hello, can you hear?
I can hear you, yes.
Yeah. Since you are talking about a partition of a number, and you told about a wonderful result by Ramanujan and Hardy. Is it P of n is equal to 1/4n√3 into e raised to pi square root 2n/3?
Sorry, I didn't understand. Can you ask again?
P of n is equal to 1/4n√3 into e raised to pi square root 2n/3.
Yeah.
Is it he obtained?
No, I'm sorry, I don't really follow. I can't recall that particular result, but I mean, as I say, some of his results were quite amazing. In one of my other books called Number Theory, a very short introduction, I had quite a lot of Ramanujan's results there, and I think I've got some of his results on pi in Euler's binary equation. Oh yes, some weird results. According to Ramanujan, pi is approximately, if you take 9 squared and then add 19 squared over 22 and take the 4th root, you get pi to 11 decimal places. Amazing result of Ramanujan's. If you take 17 plus, there are lots of other results. They're quite amazing. There's one of his results which has numbers like 1, 3, 5, 9, 1, 4, 9 plus something in, and you sum a series and you just get 1 over pi. I mean, some of his results on pi are just absolutely staggering, and it just seems amazing how they could be thought up. So I'm sorry I didn't answer your question, but you certainly...
No, since you are talking about the partition of a number,
sorry,
partition of a number.
Oh yes,
Ramanujan and Hardy given a wonderful formula, like what I told.
Yes, I have that formula in my book on number theory, a very short introduction. I can't remember it at the moment, but yes, you're right.
Oh, okay.
So I apologize for that. But if you look in that book, and I can mention actually, there's a very, very nice paper by someone called Adrian Rice, R-I-C-E. You could look up his, Google him, because he wrote a very, very nice, he gave a very, very nice talk once and a very nice article about that paper and hard. So I can recommend that you go to Adrian Rice's paper on the Hardy-Ramanujan partition formula. I can't remember the details, I'm sorry, but it's a good place to look.
One question I have, when you are in the lecture, you use the distributive property for complex number to define addition and multiplication. Is it the way? Actually, we have to introduce these complex numbers and we have to trace the properties. Before that, we have to define the addition and the multiplication. So I think it's a definition only. So after that only we have to go for the properties.
The interesting thing about how, as you saw, so many people just didn't believe complex numbers or imaginary numbers, and for hundreds of years they were not accepted. They first came up, as I said, with Cardano, and for 300 years they were treated with great suspicion. And it wasn't until Hamilton came up with like playing a game. Here are the objects. Here's how you play with them. Here's how you add them, how you multiply them. And once it became a sort of game, that stopped all the suspicion. I mean, a lot of people didn't use them, but it still was part of the. It helped to make it more acceptable to people who wouldn't accept it. Again, it doesn't really answer your comment, but I thought it was a point worth making. So,
thank you, sir. Thank you for the wonderful lecture.
So thank you anyway for asking us.
Hello, sir. Am I audible?
Yes, I can hear you.
Sir, my name is Ramakant. I did my bachelor's in mathematics and now currently I'm doing data science. So your talk was very informative and I just love the way you presented. You only use the basic notions and concepts, still explains these concepts wonderfully. Thank you, sir.
Thank you very much. Well, I try to do that. And in fact, some of this material will be appearing in these films that I'm making. As I say, they're all in Euler's pioneering equation, but as I say, I'm enjoying making these films because you really do have to try and see how, if you're explaining to school children some of these concepts, you really do have to think about how to explain it without making it too complicated. And in fact, even in this talk, I cut out one or two complicated things which I might have included. I was thinking of talking about some of other people who got formula which were nearly Euler's equation but didn't quite make it. But I thought they might be too complicated for today, and I wanted to try and make it most of it understandable. But whenever you're teaching anything, you've got to think about your audience, and you've got to aim directly at your audience. And of course, if you're giving a lecture, as I am today, to lots and lots of different people with all sorts of different mathematical backgrounds, how do you pitch it quite right? One just has to hope for the best. So thank you very much for your kind remarks.
Thank you, sir. Thank you.
Okay.
Hello.
Hello.
I'm Mukti Acharya. I'm a retired person. Sir, I was
Hello.
very happy to, are you able to hear me?
Yes, I can hear you. I can see you as well.
I'm very happy to hear your talk. It was very informative. And apart from that, the knowledge which you gave, starting from the school level, I liked it very much. And I just I want to give a reply to Saloni's question. She was asking about directed diagrams and posing some problem. So my suggestion is that she should try to read about factory nets.
So to read what?
Factory nets. It's
okay.
If you look at a graph, it gives us bipartite directed graph.
Right.
And it has a lot of applications. Basically started from chemistry, but it has a lot of applications in mechanical engineering, civil engineering. And I have guided one student on factory nets where we merged factory nets and graph theory.
Right.
So if she's hearing, she should search for that concept, and she may get the interest in doing for a PhD. So thank you very much. I'm very glad to see you and hear you.
I'm pleased to meet you too. Yes.
Thank you very much.
All the best for the future. Okay.
Yeah.
Okay. Then we can have the vote of thanks. So for the vote of thanks, I welcome Ms. Unnati Shukla. She is a PhD scholar at IIT ISM Dhanbad.
Thank you.
Thank you, Amrita. Thank you so much.
Thank you.
So, first and foremost, happy National Mathematics Day to all of you. And thank you everyone for being a part of this webinar. My name is Unnati and I am a part of this community. It is such an honor for me to get this opportunity to thank all the dignitaries, contributors, and participants of this event. First of all, I would like to thank Professor Robin Wilson for taking time out of his busy schedule to grace the event. Sir, you began with the history and introduction of the constants in Euler's equation, which was truly mind-blowing to learn about. The tour to Euler's equation that you took us to was really amazing. I've never seen this side of Euler's equation. Thank you so much, sir. A special thanks to Ms. Amrita, our host, who has managed to maintain the curiosity and enthusiasm from the start to end. I would also like to thank Ms. Rosna for introducing our speaker. Also, I'd like to extend my gratitude to Bijumon Sir, Associate Professor, MG College, Iritty, Kerala, for continuous technical support to the community. And finally, my heartfelt gratitude to the founder of this great community, Vinod Kumar Sir, Associate Professor, TMG College, Tirur, Kerala, whose initiative has connected all of us together. In the end, my thanks to our active contributors, Ms. Gayathri, Research Fellow, IMSc Chennai, Ms. Adra, Research Fellow, University of Hyderabad, Dr. Rosna Paul, Research Assistant, Fern University in Hagen, Germany. And last but not the least, a big thanks to our enthusiastic audience for joining and making this event a huge success. Thank you so much, everyone, for joining. Yeah.
Well, thank
So
you very
thank
much
you,
for inviting
Rosna.
me.
So now let us wind up the session. Thank
Okay,
you all
thank you,
for
sir.
joining.
Thank you very
sir,
much for inviting me. It's been a
Thank you,
great
sir.
honor to do so.
Thank you, sir.
And all
Thank
the
you very
best,
much, sir.
Thank you so
all the
much,
best
sir.
to all of you for the
Really
future.
nice talk.
Thank you very much, sir.
Good.
Yes, sir. Thank you very much, sir.
Okay, thank you.
Yeah, I will contact you in email.
Right, okay.
Thank you, sir.
So goodbye now.
Yeah.